In this session, we're going to cover two foundational concepts in machine learning: classification and regression. These are fundamental to how machines learn to categorize information and predict outcomes.
Here is our agenda. We'll begin by differentiating between classification and prediction. Then, we'll examine the process for building a classifier. After that, we will explore two key methods: decision tree induction and the probabilistic approach of the naive Bayes classifier.
All right, let's start with the basics. In machine learning, the terms classification and prediction are often used, but they refer to two distinct tasks with different types of outputs.
On one side, we have classification. Its purpose is to construct a model that predicts a categorical or discrete label. Think yes or no, cat or dog. This is a form of supervised learning because it learns from data that has already been labeled. On the other side, we have prediction, or more specifically, regression. This task involves modeling continuous valued functions to predict a numerical value, like a temperature or a price. The key distinction is this: classification predicts a label, while regression predicts a quantity.
Now that we've defined what classification is, let's look at how it's actually implemented. Building a useful classifier involves a clear, structured, three-step process. The process flows logically. First, in model construction, we use a training set of data where the correct class labels are already known. This is how the model learns. Second, during model testing, we evaluate the model's accuracy using a separate test set, comparing its predictions to the known labels. Finally, once the model's performance is satisfactory, we move to model application, where it's used to classify new, unlabeled data. And this diagram illustrates that entire pipeline, showing the flow from the initial training data through testing and on to a final class prediction for new data. So, what form do these classification models take? Let's begin with one of the most intuitive approaches, the decision tree.
A decision tree is a classifier that's built using a top-down, recursive, divide-and-conquer strategy. Essentially, it partitions the dataset into smaller and smaller subsets based on the values of its attributes, creating a flowchart-like structure.
Here is a generic structure of a decision tree. It's composed of nodes, which represent tests on attributes, branches, which represent the outcome of those tests, and leaf nodes, which represent the final class labels or outcomes. Now, a critical question in building a decision tree is which attribute to test at each node. This is determined by an attribute selection measure. It's a statistical metric used to identify the attribute that provides the most effective split of the data. One of the most common measures is information gain.
To understand information gain, we must first define entropy. Entropy is a measure of the impurity or randomness in a set of data. A perfectly homogeneous set has an entropy of 0, while a set with an even mix of classes has maximum entropy. The formula is stated as the entropy of a set S is equal to the sum over all classes I of negative P of I times log base 2 of P of I, where P of I is the probability of class I. Information gain, then, is simply the expected reduction in entropy achieved by partitioning the data based on a specific attribute. The decision tree algorithm selects the attribute that provides the highest information gain. The formula is calculated as the entropy of the original set minus the weighted average of the entropy of each subset created by the split.
All right, let's move from that rule-based model to a probabilistic approach. This brings us to Bayesian classification. A Bayesian classifier is fundamentally statistical. Instead of creating deterministic rules, it performs probabilistic prediction. It calculates the probability of a given data point belonging to a particular class, and it does so using Bayes' theorem. And here is the core of this approach: Bayes' theorem. It mathematically describes the relationship between a hypothesis and the evidence. The theorem states that the probability of a hypothesis H given evidence X is equal to the probability of X given H multiplied by the prior probability of H, all divided by the probability of the evidence X. This allows us to update our belief in a hypothesis as new evidence becomes available.
Bayes' theorem is powerful, but direct application can be computationally intensive. This leads to a very practical and widely used implementation called the naive Bayes classifier.
The naive part of the naive Bayes classifier comes from its core simplifying assumption. It assumes that all attributes are conditionally independent of one another given the class. In other words, the presence of one feature does not affect the presence of another. While this is often an oversimplification, it makes the computations highly efficient. This formula demonstrates the classifier in action. Because of the independence assumption, the probability of a class C sub I given the features x is proportional to the prior probability of the class multiplied by the product of the probabilities of each individual feature given that class. The model then predicts the class that yields the maximum posterior probability.
Now, what about attributes that are not discrete categories, but continuous numbers? For these cases, the naive Bayes classifier typically handles them by assuming that the values for each class are distributed according to a Gaussian, or normal, distribution. The probability is then calculated using the Gaussian probability density function.
This brings us to a final consideration. The naive Bayes classifier is built on a foundational assumption of attribute independence that is rarely true in reality. This raises an important question. What are the theoretical limits, and conversely, the practical strengths of this approach when applied to complex, real-world data sets where attributes are often highly